All right. Yeah, so hi and welcome to our first exercise course where we will talk about our first exercise sheet accordingly. Yeah, so perhaps before we start with the exercise sheet, so you can find, so this is at least my goal before the exercise course starts. I try to upload the solution, yeah. I try to take it, yeah, so to have it in PDF. I don't know whether this will work out every week, but let's stay optimistic. And then I will upload it here in our exercise course folder, where you can also find the Python notebook for the practical exercise. This is so you can also do your own notes during the exercise course or later on, however you prefer. Okay, yeah, so, and as you perhaps already saw, the slides and also the annotated slides, yeah, for each lecture will be uploaded here in the Moodle as well. So the ones for today are already there, and the next one will also be uploaded here. All right, good. Then let's switch to OneNote and have a look at our first exercise sheet. Yeah, so the first exercise sheet, well, we did not do that much in the first lecture. Yeah, but at the end we started to revisit multivariate differentiation. So the entire topic here, which fits quite well because this is a quite important concept, is multivariate differentiation. And well, what is necessary or what is a good thing to do before we start with the two exercises we have here on the exercise sheet is to have a short reminder of perhaps the most relevant tools you use in the simple univariate differentiation world. And the tools you use there are the product, sum, or chain rule, or here is it for the structure regarding the functions, which are leading then to the product, sum, and chain rule. And well, what holds in the univariate case might also hold in a similar way also in the multivariate case, not always. Yeah? So in multivariate, in the multidimensional case, sometimes things don't behave as expected, but in this case, yes, it will be as we like, yeah, that we also have a product, a sum, or a chain rule. And in order to see how these look like, yeah, so let's have a short reminder and then quickly also check that this is really true for the multivariate case, yeah, for the gradients as well. Let's see. So what we will do in order to distinguish here the univariate case and the multivariate case, so uncapitalized G and H, these are the univariate functions, so they are mapping a real valued number to a real valued number. And to distinguish this between the multivariate case, we write capitalized G and H, which are mapping d-dimensional vectors to real numbers. All right, so let's start with the sum rule. What is the sum rule telling you in the univariate case? Well, if you want to compute the derivative of the sum of these two functions, g and h, with respect to x, then it's nothing else than the sum of the derivatives respectively. Okay, sounds familiar. What about the multivariate case where we are dealing with gradients? Well, what is the gradient of the sum between these two functions, capitalized G and H? Yeah, well, the gradient is nothing else than the collection, yeah, row by row, it's a column vector, of the partial derivatives of the function we are computing the gradient of with respect to the respective component. First component of x in the first row, second one in the second row, and so on till we reach the last component. And okay, but wait, isn't this here what we see in one of these components nothing else than a univariate function? So again, what is how can we interpret here this partial derivative with respect to one single component? It is we vary only the component for which we want to compute the derivative, so x1 in this case, and all the rest are fixed. So it's essentially a univariate function. So for a univariate function, what we can do is, we can split it up in this sum structure. We can do this for all of these components, and well, this is a column vector, so we can also write it as the sum of two column vectors respectively. And what are these column vectors? Well, the first one is the gradient of G. The second one, which we add here, is the gradient of H. So we started with the gradient of the function G plus H, and we see it's nothing else than the gradient of G plus the gradient of H. Quite intuitive. All right, what about the product rule? You remember the product rule in the univariate case? We are interested in the derivative of the product of G and H with respect to X. And well, it's not simply the product of the derivatives. It has a slightly different structure. So it is the derivative of the first function G times the function H as it is, and then plus the function G as it is times the derivative of the function H. Now, this is the well-known product rule for differentiation in a univariate case. All right, what does this tell us about the gradient? If you want to compute the gradient of the product of two multivariate functions. Again, we start as before. We write down the definition, what the gradient will be. The gradient will be nothing else than the partial derivatives, where we again look at the product of these two functions and vary one component, and the raw number is telling us which component we are varying for which we want to compute the derivative. So in particular, we are looking here essentially at a univariate function which we vary in the respective component. And now, for each of these univariate functions, we can apply the product rule as we had it before for the univariate case. And what we end up with is, well, so in the first component, just to have it for sake of completeness, we have the partial derivative of the function G with respect to the first component of X times H of X plus G of X as it is times the partial derivative of H with respect to the first component. And then varying the partial derivative components that you know what you get in the other ones. Again, making use of linearity of the d-dimensional real-valued numbers. So what you could first do is you could first write it here as a sum of column vectors, where you have essentially in the first column vector this first part, and the second column vector this part. And then what you could do is you could simply use the fact that here h of x in the first column vector is multiplied to varying components. So the partial derivative of g with respect to the ith x component might vary, but the h of x, which you multiply here at each case, is the same. It's a scalar, so it's essentially also a scalar, which you could simply write in front or at the back, however you want. The same holds true here for the g of x times component. You can write it in front. The partial derivatives of the h are varying, but the g of x is all the same. So what you end up with is here at the end, the gradient of g. Now this is what remains in the column vector when you plug out the hx times hx, of course. Then you add to this g of x, which I have pulled out of the second column vector, and the second column vector is the gradient of h. So again, comparing the product rule in the univariate case and with the multivariate case, very similar, right? So you have essentially the same structure. The only difference is now that you have here a gradient instead of a single derivative. A bit more complicated object, you might say, but from a meta perspective, it's very similar. Okay, and since we are now here at the product rule, and the product rule implies, or one way to at least derive the quotient rule is the product rule. Now we will also take a look at that. So what is the quotient rule or ratio rule? It only applies in the case where the function which we are dividing with is not zero at a particular point. But let's assume this is given. Then what is the derivative of the ratio or the quotient between the function g and h? Well, it's again a bit similar, but still a bit different from the product rule. But as I said, you can essentially derive it from the product rule, because you could simply define the function f of x, gx, hx, and if you go for f of x, hx, gx, and then apply on gx the product rule, do a bit of algebraic manipulation, you end up with this quotient rule. All right. And what we see here, so on the quotient rule is, well, in the enumerator, we have the derivative of g multiplied with the function h as it is, and then minus g as it is times the derivative of h, and divide the entire thing, so in the enumerator, with h to the power of x. And here you see why we need to require that h of x is not zero, because otherwise this here is not well defined. Dividing by zero is not well defined. Okay, and well, we can again do the similar consideration, but I think you trust me right now that this here is true, right? So we have a quotient rule for multivariable functions g and h, which is, again, from a structural perspective, very similar. You multiply the gradient of g with the function h as it is, subtract from that the function g as it is, with multiplying the gradient of h, and then dividing with h to the square of x. And again, you need to, of course, require here that this thing here in the denominator is well defined, or that you don't divide by 0. This is what you need. All right. So this is good news, because sum rule, product rule, quotient rule are making things simpler in the univariate case, and as we will see also in the multivariate case. And there's also another thing, namely the chain rule, which is essentially the most general one. So you can in particular derive the product's sum quotient rule from the chain rule, but still one has oftentimes the chain rule separated from the others. And what is the chain rule telling us? So it's about the composition of functions. So when we first apply one function, and then on top of that we apply another function. So let's say we first apply the function g on x, and then apply h on the outcome of g. So sometimes we also write it here with this small circle. Perhaps you saw that in some fundamental lectures. And how can we compute then the derivative of this thing? Well, it's given in a product structure where we first look at the derivative of h with respect to g. So essentially we have the derivative of h with respect to its input, and for the input we simply plug in the value function of g. This is how you have to interpret it. And then we multiply it with the derivative of g, so of the inner function. So the structure is, you can memorize it, derivative of the inner function times the derivative of the outer function evaluated at the inner function. This is how you can memorize it. And now, in the multivariate case, we have, let's say, a problem in some sense, or not really, in fact. So, what we had was g and h, both were mappings from a d-dimensional vector to R. So, composing them is, of course, not really well defined. So in either way, h times h composing g or g composed h, both is not well defined, because first you would map the d-dimensional x to a real-valued number, but g wants a d-dimensional vector as well, so this would be not defined, and here, of course, the same. So we have here a problem when we look at the composition. But what we can do is instead do the following. So we could look at the composition h with g, or also h, uncapitalized h with capitalized h. This is what we could do, and all the other combinations, because this will be well defined. G is mapping a real-valued number to a real-valued number, h is doing the same, so each of these things, h, g, x, this is perfectly defined. So everything is well defined. And these are the compositions which are the most relevant also when computing or when dealing with multivariate functions. We will see oftentimes you express the multivariate function exactly in this way, so that you can express it as first applying a multivariate function g and then applying a univariate function on top of that. And let's, without loss of generality, let's say we want to look at the composition H and G. Yeah? We could also do the same for the other three variants, but the result will be the same. Okay, what will be the gradient? Yeah, so the derivative of this composition. First applying G, then H. Well, again, yeah, what is the definition of the gradient? It would be the partial, so collecting the partial derivatives of the resulting function. Now the resulting function is H. First applying G, then H, and then varying one of the respective components, yeah, depending on which row we are in. And here we can again use the chain rule on each of the components, and what we end up with is again outer function evaluated at the inner function times derivative of the inner function, partial derivative rather. And again, we see all these things here are not varying. Yeah? So here we have always the same value, which we can write in front. And what we are left with in the column vector is the gradient of G. So what we see here is, again, the structure outer function H evaluated at, so the partial derivative of the outer function evaluated at the inner function times the derivative of the inner function, and derivative of the inner function is a gradient, yeah, because the function G is multivariate. Again, very similar to what we had in the univariate case for the multivariate case. All right, then, last but not least, worth mentioning that this is also true for multivariate derivatives. Yeah, so if you have a constant which is not depending on x somehow, this is also what we kind of used already. The gradient of c times some function, yeah, is nothing else than c times the gradient of that function. And if we add the constant to the function, yeah, we don't actually change the gradient. The gradient still stays the same. And this has also an interpretational perspective. So recalling that the gradient is showing you the direction with the steepest increase. Now your function is not gx anymore, but it's c times gx. So what happens with the direction now? So it is scaled by this factor c. And if you add here something to that, yeah, so you shift essentially the entire function, yeah, the direction will still be the same. You just shifted the values. All right. So this was a quick reminder. So this will be our toolbox. So memorize everything here will be always be a good idea to have them present. And now we can indeed dig into the exercises. So unless they are, of course, so please feel free to interrupt me at any time. I also have to check whether, yeah, no Zoom. So the same holds true for the Zoom audience. Yeah? So unmute yourself, or if I haven't, so I cannot see the chat or something. That this is always the problem. But if there is a question, then feel free to ask it at any time. All right, so let's have a quick warm up. Yeah, this is the first function. Our first function is mapping two-dimensional vectors to the real-valued numbers. Yeah, so we could also here, of course, use any dimension d, but yeah, just as a warm-up, I decided to take dimensionality 2. And what we want to do is we want to compute gradients gradients, and we want to compute silver Hessian, so the second derivative. All right, let's start with the gradient of this function. And what we have here is exactly, or at least we can express it in this way. We could also do something different here, but what I saw directly was a chain structure, namely a chain structure where our outer function, which is a univariate function, is simply the exponential function, and the inner, the multivariate inner function is the function g, which is summing up the squared entries of our input vector. Or put it differently, it's the squared Euclidean norm of the vector x. And you see, if we would have considered the case of this here with xd square, this inequality here will still be true. But just as a side remark. All right, and then we can apply our chain rule. So we need the derivative of the function h. Well, easy going. Exponential function, what is the derivative? It's the exponential function itself. What about the gradient of g? Well, here we have to think about what this is. So what's the partial derivative of the function g with respect to the first component? Well, if we look at the partial derivative of this thing with respect to x1, it's a quadratic function, and well, the quadratic function has derivative 2 times the entry. If we look at this term with respect to the first component, and compute the derivative, this term is not depending on x1, so this is a 0. So we see in the first entry, taking this and this into account, we get this. All right, with the very same argument, just reversing these two over braces, you get that the partial derivative with respect to x2 is 2 times x2, because the first summand is 0. If you consider the derivative with respect to x2, the second one is 2 times x2. Very similar argument. And what we get is the column vector 2 times x1, 2 times x2. We can write the 2 in front of the vector. So what we have is 2 times x1, x2, which is x itself. Okay. Now everything together for the chain rule. We want the gradient of the function f. We express the function f as the composition of h, f, or first applying g and then applying h, because this is exactly what the function f is doing. Now we use our chain rule, which is telling us this. So the gradient is equal to the outer function derivative evaluated at the inner function times the gradient of the inner function. All right, we have everything together. So here, oh, no. Yeah, so here, we can use this here. So we only have to do the substitution. Instead of z, we have to input the inner function g. So this is why you have here not x of z, but rather x of gx. This is what I said, outer function derivative evaluated at the inner function. This is the correspondence you have here. And well, orange, great. What we have here, the gradient of g is 2 times x, computed already. So now plugging everything in, doing a bit of focusing a bit on the result, we see, okay, this here is again nothing else than f of x. So what we essentially get is 2 times f of x times x. This is the gradient of the function f. All right. Good. So we have the gradient. Now we want the Hessian. The Hessian of the function f. And what is again the Hessian? The Hessian is nothing else than the Jacobian of the gradient. And what again is the Jacobian? The Jacobian is nothing else than looking at the multivariate function, component-wise on the output, and then again applying the gradients, stacking them together in a matrix. And this is what we will do. And to make things more simple, we give the gradient now a new name, let's say a new label. We call it now capitalized f of x. So this here is this really the same as the gradient. I use this to make the notation a bit more easier. Always playing around with this gradient is a bit unsatisfying. So, and what is the gradient? We just have computed it here, right? So the gradient was this. So this is what we get here. Again, what is the gradient? It's a mapping from r squared to r squared. We plug in a two-dimensional real valued vector and get out again a two-dimensional real valued vector. So 2 times f of x, this is a scalar, but the x here, the x you have here at the end, this is a two-dimensional vector, of course. Okay, then let's give a name for the two components of this function fx. What is the most reasonable way to give the names? It's f1 and f2. So it's the first component of this function f of x and the second. So we can write it also in this way, right? So f of x is nothing else than stacking together row by row the component function f1 and f2. All right, and well, in order to have it really clearly what we are doing, we introduce yet another function, only for clarity reasons, that we really see that the product rule here is coming into play. We specify the function, multivariate function, which is mapping an x to a scalar, h1, and it's nothing else than forgetting about the second component, or projecting it in the first component. The second function h2 is projecting on the second component, so forgetting about the first one. And then, as you see, we can also express f1 and f2 with the help of h1 and h2, simply by replacing here at this point h1, at this point we plug in h2. All right, and then we are interested to get the Hessian matrix. We are interested in the gradient of f1 and also an f2. Let's start with f1. What's the gradient of f1? Well, this is what we are looking for, namely that we have here a product structure. We have here a multivariate function, yeah, f, and another multivariate function, h1. We can apply this product rule, yeah, that the product of these two functions, the derivative of the product of these two functions is given by derivative of the first function times the second function as it is, plus first function as it is times derivative or gradient of the second function. Now this is our product rule we had above. All right. Then we can take use of the fact that constants can be written in front of the gradient. Yeah, so the two can be written in front. And well, what remains is the gradient of f of x, but the gradient of f of x, this is the capitalized f. This is how we have called the capitalized f of x. h1 of x is nothing else than the first component of x. What about the second term? 2 times f of x. What's the gradient of h1x? Well, h1x, it's a 1, yeah, because you have here a linear function or the identity function, if you want, in the first component. So looking at the derivative, the partial derivative with respect to x1 gives you a 1. And well, x2 is not coming into play somehow for the function value of h1. So the partial derivative will be 0 there. All right, then what we do is what we do next is, yeah, I don't know why this was necessary, but what we do then is, again, the definition of f of x. Yeah, so we have computed the f of x before the gradient, and the gradient is 2 times so fx is nothing else than 2 times fx times x. Yeah, this is what we use here. Plug it in, the rest stays the same. And now we write it in a more compact form, just to realizing what is here vector valued, what is scalar valued, what is vector valued. Let's use a specific color to specify what is vector valued. So vector valued is this thing and this thing, and the rest is a scalar. This is a scalar, this is a scalar, this is also one. And well, what we only have to do then is to combine everything in a clever way. What can we do? We see, well, in both vectors, we have the 2 times f of x scalar in front of it. And what remains then is, yeah, to add the x1, x2 components to the this second column vector, yeah, the 0, 1 vector. And well, with looking a bit, focusing what is going on there, we see, yeah, we have here coming from, now it's perhaps not so obvious, but what we get is the 2 from here. Yeah, I think there's something missing. Because you isolate 2 from 4, but that means. Yeah, I think that something is wrong there. Let's see. So we have here x1, x2, we extract 2f of x. Yeah, this is what we all agree upon. Then we have the 2 still here. We have a x1 still here. And then we add here 0 and 1. So what we get is here, of course, the 2 is missing. Here, and then this should be a 1, right? Yeah. And here, of course, a 2. Yeah. Now it matches. All right, then I guess there will be, this arrow will be also later on. So we will have here a 2, here a 1, and here a 2. Yeah, so if you do the same calculation for this F2 gradient, yeah, with a similar reason, yes, just reversing the 2 is quite symmetric, we will get this one. And the Hessian, which we get by looking at the gradient of the F1 function, stacking it row and row by row with the F1 and F2, we get here 2, 2, 1, 2, 1, 2. Yeah, we'll take care of the that I will upload here the correct version. Yeah, but now it should be fine. All right, so this was a quick warm-up. Now let's have a, or are there anything, is there anything unclear? Everything fine, very great. Good, then let's go to number 2, function number 2. So yeah, let's go over it rather quickly because it's more or less quite straightforward from what we did before. So we can again express this as a chain structured function where we have as an outer function, outer univariate function, the logarithm, or rather 1 plus input and then the logarithm, and the inner function which we apply, which is a multivariate function, so it gets d-dimensional vector, puts out a real-valued number, is x transpose x, or again, this is nothing else than the squared Euclidean norm. This is why I also referred to the previous exercise as a warm-up, or the previous part. All right. So what is the gradient or the derivative of this outer function h? Yeah, logarithm 1 plus z is 1 divided by 1 plus z, where you essentially already apply the chain rule. Have to be very rigorously, but all right. And the gradient of g, so we can do the same argument as before. Yeah, this is why I gave here the side remark that we could also here do the same with summing up till for d components, the squared. You will get the same structure as before. Yeah? So only one component is depending on a specific x value, xi value, yeah, and it's depending on it in a squared manner. So the derivative, the respective derivative will be 2 times the component, which you can again express as 2 times x. What we use then is the chain rule again. Yeah, we have our chain rule structure here. We have the derivative of the outer function, where we plug in the inner function for the z. We have our, just to have it in line what we had before, it was orange, right? Orange was the color. We have this one, and well, we can compactly write the gradient as 2 times the vector x divided by 1 plus the Euclidean norm, or if you like, also x transpose x, the inner product of x with itself. All right, what about the Hessian matrix? Now we want to compute the Hessian matrix. We again specify the gradients or refer to the gradient as this capitalized F function to make things notationally more simple. And we also refer to the denominator, which the function which is in the denominator. We refer to it as the function h of x. So 1 plus the norm. So it's again, this here is mapping from RD to R, right? And the gradient itself is a mapping from RD to RD. And now let's have a look at the components of this function f of x, so the gradient of the small f. And what is this? Well, what is vector valued and what is scalar valued? We can again distinguish here what battery is. We can distinguish what is vector valued versus what is scalar valued. This here is a vector, this here and this here is a scalar, right? So again, vector, scalar. So if we look at the components of this vector, we see the components are determined by the components of the x, of the vector value, and everything else is just multiplied as a scalar. All right, so we want to compute the gradients of this function of these functions fi. Now let's simply use or start with f1, f2, and so on will be quite similar. And what we have here is the product rule, but rather quotient rule, what we can use. So because f1 of x can be expressed as a function where we have in the enumerator the function which is projecting the x onto the first component, and in the denominator we have the function hx. We can apply the quotient rule. So again, recalling quotient rule, we have in the enumerator gradient of the first function, which is 2 times x1, multiplied with the function in the denominator, h of x, minus the first function, and so the enumerator function as it is, times the gradient of the denominator function, and then everything divided by denominator function to the squared. All right, now what we can do is, or what we need to do is, we have to compute these two gradients occurring here. What about the first gradient? So the gradient of this function, which is projecting the value or the vector x onto the first component. We had it, so we referred to this function in the previous part as the h1s and h2s. So these projections, we saw quite quickly that the gradients are nothing else than unit vectors. So here it's again a unit vector, namely one where we have a 1 at the first part, and then, so just to make it very clear, everything else is 0. What about the gradient of the h function? So the h function is 1 plus Euclidean norm, and well, 1 plus Euclidean norm, we can also express it like this. So h of x is this. But well, we can forget about the constant, right? You remember? This was the rule. And if you look now, what is this? This is the function g of x we had before. Yeah, so x transpose x. This is the function g we had here at the beginning, yeah, the orange one, which is simply the Euclidean norm, or x transpose x. And for this, we have here in orange computed that the gradient of this function is 2x, right? This is 2x. So, long story short, the gradient of hx is 2 times x, and this is what we used here. All right. Then again, just to make sure that we stack everything together in a correct way. So, well, we have this h of x squared in the numerator. We have a 2. We have a 2 here. We have a 2, let's say here, which we can also write in front of that thing. And then the rest, what is the rest? Well, we have here a vector which has in its first component h of x, everything else is 0, and we subtract from that the vector x multiplied with 2 times x in its first component. And well, this should be the result if we put everything together. Well, this time I don't think there should be a bug. And now we did this only for the first component. Now, what about the second component? Well, the only difference will be in varying the component 1 will be where we have this one here and this one here. So substituting here the one with some other index I will only lead to the fact that this unit, the first unit vector you have here is becoming the ith unit vector, and instead of the first component of x, you will get here the ith component of x. And okay, I used j, but now substitute I with j. And what we end up here is a similar structure where we have then in the jth component, so this is the jth component, and in the other components we have a similar structure as before. Here the xj is coming into play, and here we have the square. All right, then putting everything together to get the,
I think there's a type on the last entry of the matrix, which should be minus 2 times h of x.
Oh, yeah, thanks. This is, thanks. Everything, so putting everything together, so row by row. This is the first row we explicitly computed. The second, third, and dth row, well, you can check that this will be indeed the gradient of that, where at the jth component, or in the Hessian matrix, eventually at the diagonal, you have this hx component, hx minus something component, which you see here. And well, what is also quite nice to check is then, is the matrix symmetric? Because quite obviously the function we started with is continuous differentiable. So, I mean, most of the functions we will deal with are continuously differentiable. And you remember that in this case, the Hessian matrix is symmetric. So this is also a sanity check every time, whether you computed everything correctly. And we see here, yes, the Hessian matrix will be symmetric. All right. Good. Then except I have here somewhere a bug or everything, something's unclear. I would go to the next one. So let me quickly check whether in Zoom everything is fine. Yeah. All right. Then in the third part, we have this beautiful function here. Yeah. Mapping d-dimensional vectors to 1 over 1 plus x, and then minus inner product of some fixed vector a and the variable x. So in machine learning, this function is actually quite common. It's the sigmoid function, which you have in logistic regressions and so on, if you're familiar with that. If not, not so important. We will have a look if necessary. And again, we can extract here a chain structure now. So at least this is how I saw it directly. You have the outer function h, which is a univariate function, which is 1 over 1 plus x of z. And then for z, what you need to input is the multivariate function g of x, which is the inner product of this vector a with the x. All right, so it's a bit quick, but I mean, we can also apply here the quotient rule if you like, yeah, for the hz to compute the derivative of h with respect to z. Now, just to make sure that this is really true. So what we have for h is again a quotient structure, right? So where the function in the enumerator is always mapping to 1, and the function in the denominator is 1 plus xz. All right, then what you will start with is the derivative of the enumerator function. It's a 0. You multiply it with the denominator function. You subtract from that the enumerator function as it is and multiply it with the derivative of the denominator function, and the derivative of the denominator function is xz. And then you divide it, the entire thing, with the denominator function to the squared. And voila, what we see is xz 1 plus xz squared. Yeah, so everything's fine. What about the gradient of the function g? Yeah, what is this here? So actually we also had it in the lecture, but it does not harm to have a look at this again. So what do we have here? It's a sum over these things here. And now looking at the derivative with respect to some component, you see only one summand is relevant for this partial derivative, namely the respective components. So let's say j, then the jth summand is relevant. And what will be the derivative with respect to the jth component? It's then the factor, so the scalar with which you multiply the jth component, the x component, and it's then aj, or minus aj rather. Now you collect this all together, and well, this is nothing else than the vector a. All right, then we can again apply the chain rule. Here we have this thing here. We plug in for the z, the inner function. Should I scroll it up? Oh, all right. The gradient, orange was the nice color. Memorize this. Is here, and well, yeah.
Shouldn't that be a positive number afterwards, because we have the minus exponential function, then minus a, and then we should have, or am I completely wrong?
Oh yeah, sure. This should be a, yeah. Thanks. I guess this will be later on also. Yeah, okay, but yes, you're right. Yeah, so you see, I was a bit in a hurry when I tested. This is why I actually don't like it to take it beforehand, because, but well, I mean, this is for the exercise course 4, because I can also check whether you are paying attention, of course, and you obviously are. All right, exactly. So the minus here was not correct. What we get here is, well, a vector, so just to stay in line with the considerations we had before, scalar. And now we can make things quite simple, actually, or write it really conveniently afterwards, if we realize the following. The scalar you see here can also be expressed as 1 minus f of x times f of x. Why? Let's have a look at what 1 minus f of x is. So 1 minus definition of f of x, you get this here. This here can be expressed as 1 plus x minus a transpose x divided by the same. Yeah, so this is a complicated way to express a 1, or the valid one. Yeah, putting everything together, you see, well, the 1 and this minus 1 here are canceling out. You're left with x of minus a transpose x divided by this function we have all the time in the denominator. And well, if you multiply here f of x, you see exactly this thing here encircled in green, right? So this is our favorite representation of the gradient. Yeah? So we will see why this is. So we could also stay with the representation as it is, but it's not so convenient. All right, then we go to the Hessian. So due to the time. So, of course, this should be a plus, right? And here will be always pluses. So we have our gradient notation. F of x is the gradient, which we can express like this. We look at the components of this gradient function. This is a vector, the rest is a scalar. So the components of this function f of x are essentially given by the components of the vector a. So f of x is nothing else than stacking together these f values. And now we have here everywhere the wrong sign. It should be pluses, or
I think somewhere we need minus again, because it's from the chain rule, and when we get the minus a out of.
Let's see. Okay, so
I think at some point it's right again.
Okay, so here we have a plus, right?
Yeah.
So here it's still a plus. Then what we do, it's a scalar. A of I is a scalar with respect to x. We can write it in front. What we left what we are left with is gradient of 1 minus f of x product f of x. So this here should be also a plus still. All right, we apply the product rule. So first function is 1 minus f of x, the gradient of that thing, times the second function, which is f of x as it is, plus 1 minus f of x. This bracket here is not needed, times gradient of f of x. All right. This gradient here, yeah, 1 is a constant which we add to this. We can forget about the constant, and then we have a minus. So here is still a plus. Then we have this minus f of x, yeah, which we can pull out. So it's a constant term in the gradient. We are left with this. Everything fine here. So 1 minus f of x times the gradient. Then recalling that this here is denoted by f of x, and this is the same here. All right, so here the plus is also still valid. And then what we do is we pull out the f of x. Yeah, we have it 2 times here in this sum, and we get it here. What we are left with is 1 minus f of x minus f of x, but there's still then a plus. All right. So plus ai times 1 minus 2 times f of x times capitalize fx. Or did I think this is fine, because yeah. So if you have something,
I went completely differently. I didn't try to express the first derivative as fx, but I just converted it into the hyperbolic cosine function. And so I dropped the minus altogether.
yeah.
And
Also one possibility. Cool.
But like is the way I've understood it so far is like we've tried to express it as a term of f of x, so that you can reuse the previous gradient. That's the whole point.
Yeah. I mean, what's the nice thing is of this expression, if you write it out, is this is ai 1 minus 2 times fx times a times fx 1 minus fx. So what you have here is essentially only the function f as it was. Yeah, this is all you need. This is somehow a nice property. This is also yeah, exactly. So you can always reuse the f of x if needed.
What I've noticed, like later on when you had the code and compute the example, that when you use a term that isn't exactly like the hyperbolic cosine, then you actually get a higher difference compared to what Torch could derives.
You mean then in a Python notebook?
Yeah, that's later on when we had to use exactly our formula.
Yeah.
And like we didn't have to, but I did. Like we had to compute a gradient via Torch, like
Yeah.
That it should compute the exact value. And then I tried plugging in like the exponential function.
Yeah.
As expressed in the gradient.
Shall we talk about it when I have the notebook? I think this is so. I just want to, I think conclude here. Well, I mean, we don't have the time to go over this. I mean, you have the solutions here, yeah, so you can check whether it is. So, I mean, the structure is here quite simple. So the last function is actually one of the simplest one because you actually use here the sum rule, yeah? And also the Hessian matrix is quite nice to compute because at the end it's nothing else than T times the identity matrix. So just as a side remark, this function you see here is related to the, so also coming from the machine learning world, it's nothing else than the squared loss, what you see here. Yeah. So if you are interested in minimizing the squared loss, what you have here, and also taking into account what we had in the lecture today, is the Hessian matrix of the squared loss function is T times the identity matrix, which is a positive semi-definite or positive definite even matrix, yeah? Because what are the eigenvalues of this thing, of a diagonal matrix? It's the diagonal entries, so T, which is positive. All right, then we have the second exercise, Jacobian matrix. I mean, well, this is also just for practice reasons that you get familiar with partial derivatives. Actually, this was one of the easiest, as long as you know how to compute derivatives of sine and cosine. So perhaps one last single side remark. If you forget how to compute sine and cosine, or how the derivatives relate to each other, I guess you are all familiar with the fact that cosine at 0 is p half, right? That's one. Sorry, not p half. It's 1. But at p half, it's 0. This is what I wanted to go for. So cosine is, yes, somehow 10 here down. And you know that the sine is at 0, 0, and at p half, it's going up, right? Yeah, not like a line, but rather something like this. Yeah. Okay, now recalling what a derivative is telling you, yeah, so also regarding the slope of the function, what you see is cosine is going down. So the derivative should be negative, right? Okay. You know vaguely cosine, also derivative of cosine is sine with perhaps a different sign, -1 or +1 multiplied, and the other way around. But you don't know what exactly the, whether it's -1 and 1 is. So if cosine is going down, yeah, but sine is at this interval positive, well, what should hold? The derivative of cosine must be minus the sine, or other case, sine is going up, so the slope must be positive, but cosine is also positive on this range. Yeah, so derivative of sine is cosine. Just as a side remark, if you ever forget the relationship between the derivatives, this is how you can always recall how they relate to each other. All right, so as I said, yeah, so have a look at the solutions. I will take care of the 2 bugs we had there, or 3 bugs rather, but I mean, overall it should be fine. And now let's have a quick look at our Jupyter or practical exercise. Yeah, so it's always important to also have practical exercises, at least in my opinion. And well, what we can, so this this exercise sheet is about, also actually it's exercise 3, right? Yeah. Exercise 3, it's so you can also calculate derivatives in Python. Yeah? So good news, you actually don't have to compute derivatives at all. Yeah? So the computer is doing that for you. So by the way, can ChatGPT also? So if you ask ChatGPT, what's the derivative of, I don't know, this function, text? Is it?
When it comes to technical subjects, ChatGPT actually beats the average.
Oh, really? Okay.
But sometimes it puts like really weird and easy errors in, so you still have to be very careful when you when you ask and like think about if it makes sense.
I see. Okay. Yeah, so we still have a need to compute derivatives on our own, although computers and algorithms are helping us a lot. All right. So let's have a short or quick look at what we can do in Python. Yeah, so I use Python here for various reasons. In machine learning, it's quite common to use Python. I'm also a big fan of R, but I guess I'm the only one here, at least one of these ones. All right. So what we want to do is we want to get familiar with this PyTorch package. So we could also do this in NumPy actually, but PyTorch is giving us a quite convenient way to do this. And what we want to do is we look at this univariate function f of x and compute its derivative evaluated at some value x equal to. Okay, this is the usual way how you start your Python notebook. You load your needed packages. So we will plot something later on. This is why I have this matplotlib pyplot here. PyTorch, this is the package we are interested in. And NumPy will be later on also used, which you usually abbreviate with NP. Now, so this is somehow now this golden standard to do this. Okay, and then what you have in Torch are these tensor objects. And tensor objects are something like a NumPy. So if you're familiar with Python and NumPy or even pandas in Python, this is something similar. This tensor is also a data structure quite similar to the NumPy ND array or the pandas data frame. You can do different things, and what we will use here for the time being is only to store this value x of 2. Which you will use later on to compute the gradient. So you have here an additional parameter for a tensor object, which is specifying whether we will use this somehow to compute gradient derivatives. You can also change this later on, by the way. So if you haven't specified this here, it's also I have to reload it, of course, again. So if you do this, and then you can while grade no, I'm not in R. This is this. So you can change it later on with this. All right. Let's stay. All right, and this tensor, well, this is some tensor. This is how you get it printed, and with this tensor, you can essentially then express your function of interest. later on it will be loss functions. Here we have also only toy examples. And well, what we do is we simply express the function we want to have. Yeah, so this polynomial here with this x, yeah, using the standard notation in Python, I would say. And well, what will happen is if we look at the y, we get again a tensor. Yeah, so we have started with a tensor and made here some manipulation of the tensor. Yeah, so in the typical mathematical way for Python, and we still get a tensor. Yeah, so the y is still a tensor, and already evaluated at the value 2, which we have started here with. Yeah. So if you plug in here the 2, what we will get is 2 times 2 to the power of 2. It's an 8. Minus 2 plus 2 cancels out. It's an 8. And what we want to do is we want to compute the derivative. And what you do, what you have to do then is to call this backward function on your tensor object, which is representing the function you are interested in. This is essentially doing the derivative computation. And well, we can also check then again. So it will be back or stored back to the x, so to the tensor we started with, and will be stored in the grad field, in the grad variable rather of the tensor, which we can plug out, and well, the result will be 7. Well, we are skeptical. We don't trust machines and algorithms, so we have to check what is the derivative. Well, we compute it quite easily. 4 times x minus 1. We plug in the 2, and then okay, we are satisfied. 7 is indeed the correct one. Then we wanted to plot the function, and then we see here then the nice flexibility of the torch object, so that we can also have here essentially a range of different values. So a linear space from -2 to 2 with 100 points. This is what is telling you here. Again, we will use this later on to compute gradients. This is fine. We store it again into a function or a torch expression, which we call y, as we will use this later on for computing gradients. We also add here the sum, do the backward operation to compute the derivative, and the nice thing is everything here will be stored in the y, so the values of the function y. And well, if we look at the detached numbers, the detached list of the tensor, store it or convert it into a NumPy list, we get here. So perhaps we'll have a look what will be that one. Oh yeah, I'll cut it out. You will see here the linear space, so what you would expect in a NumPy array list. What will be the detach thing? it will be also a NumPy array list with the corresponding function values you have here. What will be the y thing? It's a tensor evaluated at, well, the sum value of this thing over all possible x's. All right, and what we get at the end, yeah, is the function value itself, which we have here in red, and the derivative, which is stored in the grad component as before. Yeah, around here, of course, the value, so some default value, which we can also change later on, but well, we have used here the default one. Yeah, so we could also compute the derivative at different points. So this is, by the way, the first Taylor approximation, of course, right? So the green line is now the first Taylor approximation of this red function here at the point, I guess it's 1. Should be 1. All right, then this is where the problems came later on for the higher orders. The last one.
I just checked this similar accuracy. I used another formulation.
Okay, so perhaps due to the formulation, it's then.
Probably was a square of dimensions.
Okay, I see. Okay, so what we can also do is, of course, yeah, univariate functions cool, but we want multivariate functions. So let's have a look at the multivariate function from the first exercise. Oops. From the first exercise, and evaluate it at a specific point, yeah, for x1 and x2. And well, it's very straightforward. Instead of a single value, we plug in here a list with the values where we want to evaluate it at 0.5 and minus 0.25. And well, we express again or create another torch object with the according function we want. And we have an exponential function, and of course, torch is giving you the possibility to express an exponential function. So you have also the sine function here, you have the sine hyperbolicus function here, you can have the logarithm function also with different bases. I don't know what's also perhaps a gamma. No, gamma is too heavy. Which one?
A square function.
Square you have also? Yeah, okay, so square.
Squares elements.
Power is not, but okay. But power is really also polygamma. Yeah, so you see there are different functions available, and if not, you can also create it on your own. Yeah, so you can also specify the function with the user specified in a user specified way. All right, then essentially same as before. Yeah, we look at the backward operation, and then the gradient evaluated at the x points here is computed, and what we get is, well, first, so the gradient at that point is that, and gradient at in the second one is that. We can again check it, and we will find out, well, it's indeed the correct one. So I don't go into the details for the sake of time. So the third one is perhaps also quite interesting with the sigmoid. So you have two ways to do this. The first one is for each of the components, you create an tensor object for the first component of x, for the second, and for the third. Then you specify your function f, which we called before y. So to be consistent, you can do this as follows. And then look at the gradient one by one, x1, x2, x3, and then you have it here. We can again do the sanity check, but you will see quite quickly it's the same what you have here. An alternative, more compact alternative is again use here a list or an array for the x values you want to evaluate and write it again in this more compact manner. And what you then get at the end is again a tensor where everything is in one list. Perhaps a bit nicer because you can imagine if you have a high dimension D, this here is a bit cumbersome. This here is more compact. No, it's a problem. All right, so this was a very short introduction to PyTorch. We will come back to that later. I picked up PyTorch because this automatic gradient computation is quite convenient, and we will also use this later on. All right, so again, almost punctual. So I would ask you whether there are questions, etc. Also in the Zoom chat, nothing there. All right, so we have finally managed our optimization for machine learning day. What is a long day to the lecture and tutorial. So I thank you very much for being so careful with the solutions. I will upload it later on, and see you then next week. Have a nice day. Bye-bye.